Hello and welcome back to Python. So here we have what we were lastly messing with, right? If you recall us from the second video, this is the temperature profile for the bar, right? Something I want to show you guys is the importance of this dt value, right? Kind of skipped over it, but if you recall, we said that we want to limit the maximum time step to 0.5. Why is that? Well, let's see. What happens if we put in 0.3 or 0.4? What happens? Well, nothing crazy. Still get a decently reasonable looking graph, right? Now let's go upwards. Let's just go straight to 1. Temperature or time intervals of 1 second. Whoa, this is completely wrong. This is saying that it goes up to values of 6 times 10 to power of 223 degrees Celsius and negative respectively, which for this situation is nothing but absurd. This is definitely not right. So let's go back and put this down, let's say 0.8, see how it reacts with that. Still very bonkers. Goes up to 4 times 10 to the 160th power, which is again absurd and not possible for this situation. So let's go ahead and go back to 0.6, keep bringing it back down. We see that it's still very wonky. It's not perfect, or it's not as insane as it was before, but it's not even close to being perfect at 1 times 10 to the 66th power of degrees Celsius. So let's go back down to 0.5. Does that bring it back within normality? Yes. Well, what is it then? Is 0.5 the threshold? Well, let's try 0.55. We see we get some bonkers with that middle threshold as well. We get values of up to 2 times 10 to the power of 34, right? Absurd values. How happens if we put 0.52? Again, absurd values. And we can do this all the way down to 0.5001. Oh, it's starting to look good, but yeah, if we keep 0.5, this graph temperature profile goes back to normal. And why is that? So let's go ahead to the whiteboard and check that out. So why exactly is this happening? Well, I'm going to take you guys through a von Neumann stability analysis to illustrate the limit of stability on the explicit differentiation that we gained in the previous videos. If you notice on the whiteboard, you see at the top we have our heat diffusion equation that we derived in the first part of this video series. And right under it is the explicit differentiation that we gained in the previous video and that we were messing with in our Python code. If you look up here to the top right, that is a new equation you guys haven't seen. It is the solution to this problem. I'm not going to take you guys through the whole process of how we determine that. Just know that this is the solution for any t within this equation, and that the k is interchangeable through all of the values. So what we can do to illustrate the limit of stability is plug in this t for all of these values and then go from there to determine why 0.5 is our upper limit. So let's go ahead and get started. Like I said, the first thing we want to do is get all of these terms, all 3 of these in this terms. So I'm going to start off with the first one, most simple, j again. And now, one thing that you guys need to remember is that we are not using x and t's. Instead, we gotta remember about our methods of incrementation with j and n, as well as our actual distances and changes. That meaning our x value is actually our what we used in our previous equations, which is, I'll show you guys here. So for the first exponential, we have I, k, which remains the same, of course, okay? And then for our x becomes our value of incrementation, j, multiplied by the distance, delta x, right? Then again, we did the same thing for time, right? The increment of time is gone through n, and then we're using delta t. So that I exponential is equal to, in this we can see is alpha k squared, that remains the same. And then the t becomes, like I said, the incrementation of n, and then delta t. Alright. Nice and simple, that is our value for our first and basic one. So now what we have to do is find it for j plus 1 and j minus 1. Go ahead and start with j plus 1, which is the easier of the two in my opinion. And all we have to do, if you notice, n remains the same, so the second exponential remains the same. The only thing that changes is the j value. Well, our incrementation is changing. Well, the distance, delta x, isn't changing, so all we have to do is add this j plus 1 in parentheses, right? As our j value is increasing by 1, that's all that's happening to this expression, right? And if you guys may notice, actually, these two are exactly the same. Like I said, Ben is not going to be touched, so the second exponential value is the same. If you may notice, the first one is also very similar. Like I said, we're only adding one value to j, so what we can do is multiply this out, as this e is actually ik j delta x as well as e ik delta x. Right? Notice ik j delta x is in RTJN. So what we can do is simply equal this to this first one and only multiply it by this exponential. Right? So this j plus 1n is now t of j of n multiplied by the exponential e I k delta x all multiplied. Right? Nice and easy. Then what we're going to do is the same thing for j minus 1. I'm going to go ahead and put this here. And actually what we're going to do is simplify it. It's going to be the same thing here that we did, except this plus is become a minus. So we're going to have this whole thing just to this exponential being negative. So we'll have e to the negative I k delta x multiplied by our common j comma n. Beautiful. So now what we can do is plug these three values into this equation for us. So we get, and go from there. Blue. So for our first value, we're going to keep our rn out. I'm actually going to bring the exponential back so that we can multiply it out, so that we'll have r e to the power of I k delta x multiplied by that time component. And then we're still going to have this middle value is going to stay unchanged, of course. So now 1 minus 2r t n, and then of course we're going to have this value times r on the last one. Plus re negative I k delta x multiplied by the temperature, and then of course is equal to the temperature at that point at the following time increment. Alright, n plus 1. Beautiful. We'll start erasing and clear up some space up here so that we can work it out a little bit better. You guys can see that? Yeah? Okay. Okay. What we can do now is simply bring out all of these common vectors out, and I'm actually going to put this to the left hand side so it's going to be easier to mess with. So we bring this out so that we have Beautiful, and I can go ahead and erase this too now. Alright, so what we can do from here is actually go back to some basic calculus math, right? If you remember Euler's formula, or Euler's, whatever you want to call it, E-U-L-E-R, we all dealt with him and his formulas for when we deal with exponentials. To this power, we know that e to the power of I x simply equal to cosine x plus I sine of x. Alright, and in this situation, our i's are I, and our x is actually k delta x, so we'd have cosine k delta x and sine k delta x. However, you notice we also have a negative I, and what that deals with is just a negative x. To put that in here, so what we have is our cosine remains the same, but our sine switches signs. Funnily enough, so we have cosine x minus I sine of x, right? And of course, we can go ahead and plug these values in for our exponentials, right? That we end up with, of course, we're going to have j to the n plus 1, and we're going to keep this on the out. And then, actually, instead of working this whole out, if we think about this, we have, we're going to multiply it by r, obviously, and the top would be r cosine k delta x plus I, or r I sine k delta x. And the same with our negative, right? This would turn into r cosine k delta x minus r I sine k delta x. And what that means is that these two sine values cancel out, and the two cosines add up. So we'd have r cosine k delta x, that turns into 2r. So we have 2r of cosine k delta x. Alright, that's for these two, and then of course we're still going to have this 1 minus 2r. Okay. Yeah. Okay. And then from here, we're pretty much there, right? Well, what this means is, yeah, we're pretty much there. Well, as you can see, we've gotten to this point of 2r cosine k delta x plus 1 minus r, and we're going to have these two values. And this is where we've kind of gotten to where we can divide this side, and that we get our kind of ratio between the two, that this middle term has to be between values of -1 and 1, as those the two limits that could possibly be. So that being said, I'm going to go ahead and put that under simply this middle term, so that we have 2r cosine k delta x plus 1 minus 2r. And then of course this has to be greater than -1 and 1. Okay. Sorry, I missed these signs around. I hate these signs, sorry. Right in the first time. No. What am I doing? Alright, so like I said, it has to be between negative 1 and 1, right? What we can do is kind of simplify this out. This middle term, make this 2 r's all on the same side, so that we end up with 1 plus 2r, and we have cosine k delta x minus 1. Alright, yeah, and then this, of course, greater than, smaller than 1, and then what we can do, see this 1 in the front, and subtract both sides, take this out, so this becomes negative 2, and then this becomes, just without that 1, so we have 2r of cosine k delta x minus 1. That has become 0 now. Took 1 out of 1, that's 0. Right. So we ended up with this. Now what we can think is this middle term here, right? Or actually look at this whole term. Well, we know that 2, of course, positive constant, right? And we also know what r is, right? We know, I'm actually going to go erase this, we don't need this anymore. To recall what we had r as, r is equal to alpha times delta t over delta x squared, right? These are all constants, right? These are all positive, and that means that r is a positive, right? And then, so what we have left is this middle term of cosine k delta x minus 1. And if we look specifically at cosine, we know that cosine of any value has to be between negative 1 and 1, right? And let's look at those situations, what would happen. So if we had if we had a positive 1, we'd have cosine go turn into 1 minus 1, it becomes 0, 0 times 2r, whatever it is, becomes 0, so that clearly satisfies this, that it is equal to 0. Now for the lower limit, if we go reach negative 1 for cosine, we get that this turns into negative 2, or some kind of large negative entity, and negative entity times positive constant, that turns into a negative, so that of course also satisfies this equation, saying that no matter what value for cosine we get, it will be smaller than 0. So we can actually get rid of this hand side and only focus when 2r cosine k delta x minus 1 is greater than negative 2. And I'm actually going to free up some space so we can go back, or I'm just going to go here to the side so we can go erase this after. Quick step, you can see we have a 2 on both sides, right? Clear as day. We just divide by 2 so that we end up with negative 1. Okay? Has to be smaller or equal to r, and that whole mix of cosine delta x minus 1. Alright, that's what we get. So I'm going to go ahead and erase this whole side so we can keep on with our... So let's continue this von Neumann stability analysis, right? I'm going to put this up here. Get a better look at it. Alright, beautiful, we're almost there. Pretty much done. So now what we can see is that we have r on this side, and what we can do is get it on its own. We can divide both sides by this second factor of cosine delta x minus 1. Actually, what I'm going to do is to get rid of this negative 1, I'm going to inverse it. And, of course, I'm going to inverse the sign and the denominator, so that we end up with sign will get inverted, right? So look like this. We'll have r always on the right side, and then this negative 1 becomes 1, and then this is inverted, so we have 1 minus cosine delta x, or k delta x. was gonna say, I don't know what happened here. I don't know how I lost this with big K sign. K delta X. Sorry. I don't know what happened. Alright, so what we see is that R has to be greater than or equal to, or has to be equal to or smaller than this left-hand side value, right? So let's go ahead and solve it. Well, again, like we said many times, what can cosine be? Cosine can go from -1 to 1, right? So what happens if we were to plug in, if we were somehow to get 1 for a cosine, then we'd end up with 1 over 1 minus 1. And 1 minus 1, that obviously reaches 0, and we'd have gigantic numbers, which explains as to why we get such high temperatures in our graphs when we go over 0.5 in our R value. And then, meanwhile, if we were to get -1, then we would end up with 1 over 1 minus -1. Of course, two negatives make a positive. This becomes 1 plus 1. This becomes 1/2. 1/2 has to be equal to or smaller than 3. As you can see, this is what we reach. 1/2 has to be, or R has to be smaller than 1/2, and that is our stability analysis. And this is, as we've seen before, when we get greater than 0.5, like I said, we get 1 over 0, which gives us extremely high values for our temperature. And if you actually notice, why this is, or why this happens, is for our R value. Well, when we plugged in for Python, our alpha and our delta x values are both 1, right? So 1 over 1 squared, that is 1 over 1, so that our R value is pretty much dependent only on our delta t. That is why when we change our delta t value to greater than 0.5, our R value is also greater than 0.5, and that would cause such great problems in our code. So hopefully this was a good use to you guys, and I'll see you in the next video.